So we know that high voltage battery systems will be more efficient than the low voltage battery system according to our calculation. So instead of a low voltage battery system which is going to produce high current, it is always preferable to have higher voltage battery systems. Let us know more about electric vehicle battery packs, and we will also discuss about why high voltages and low voltages are required to be linked by a DC-DC converter. So if I take the overall efficiency of a vehicle, and if I do this assumption of stage-wise efficiency, so here let me assume the first stage from battery to power converter is going to have some efficiency, that is efficiency 1 of stage 1. Then power converter block itself will have efficiency 2, and the electric motor will also have the efficiency which is denoted by efficiency 3, and here there will be something called gearbox efficiency or mechanical power transmission system efficiency as well. So if we talk about the flow of power from battery to wheels, there are many different stages, and if I assume fairly that all efficiencies are 80%, which means this is 0.8, this efficiency 2 is also 0.8, which is basically 80%. This is also 80%. Now what is the overall efficiency from battery to wheels? So these efficiencies are actually connected, or this effect of efficiencies are going to be cascaded and such that they will be multiplied with each other, right? So if you have the gain of the individual blocks connected in series, you can easily calculate how much will be the output in the final stage. So if you multiply 0.8 with 0.8 with again 0.8, your overall efficiency is only 51.2%. So basically, even if all stages are 80% efficient, the overall efficiency from battery to wheels will be reduced to 51%. So this is the effect of efficiency, and why it is taken care in case of battery electric vehicle, because the onboard energy is very less. And now if you consider that this battery is going to run the auxiliary power as well, right, and there are going to be a DC-DC converter over here which will draw some amount of power, and this particular load which is extra than the propulsion load will also discharge the battery. So look at the effect on the battery power rating. So for example, if you need let's say around 50 kilowatt hour of energy, right, so on the wheels per 100 kilometers, right, so here we are assuming some number that 50 kilowatt hour amount of energy is required by the vehicle to run for 100 kilometers. And now if you take the energy efficiency of all the stages and multiply that, the battery kilowatt hour may be as high as 80 kilowatt hour. So instead of 50 on wheels, now you are using a very high energy or a very large battery pack which is 80 kilowatt hour, and therefore these systems needs to be very, very efficient. So if they are less efficient, then it is going to actually hamper the overall efficiency of the vehicle, and larger the battery pack, higher is going to be the cost, higher is going to be the charging time, and there are other disadvantages as well for a large battery pack. But when we consider the high voltage traction battery pack, then the efficiency of this particular stage, where we consider the efficiency of the connectors and the wires used over here, that is going to be far better, right, than a low voltage high current type of a battery pack. So let us now move ahead and have a look at the electric vehicle battery pack, how electric vehicle battery pack is considered, or how electric vehicle battery is actually made. So let's see this basics of EV battery pack. So usually one lithium ion cell produces only 3 to 4 voltage per cell, and actually this is very higher compared to a lead acid battery cell which produces around 2 volt per cell. But now lithium ion batteries or the basic element of a lithium ion cell can produce double of that voltage, and the capacity is also higher compared to the lead acid battery, keeping the volume same. So how the EV batteries are made? So usually these cells will not be able to make it possible. So your cell phone is going to have one cell. Your laptop battery pack may be having 4, 6 or 8, 10 number of cells. But an electric vehicle requires 100 or 1000 number of cells. So these cells are configured into different modules, and for EV application, the battery pack will be consisting of multiple number of modules. So this is the way in which the battery pack is made, and let us see some of the example. So if I give you an example, so a 12 cell series with X number of parallel cells in each module, and if there are 8 such modules, the entire battery pack will be around 96 cell series, and that is going to produce around 400 volts. Let us understand it clearly. So imagine that I am taking 18650 popular battery cells which are cylindrical in shape, and I am assuming all these cells are positive from the top. Now I have taken 6 cells and I am going to connect all this positive together like this, and all the bottom negatives together like this. So the red colors are actually the wires which are connecting this. Now how do I make a larger battery pack? This can be similar to your power bank which you usually charge your phone from. How to build a larger battery pack? We need to connect more number of cells in series. So this is a 6 parallel group, and we will call this as a 6P. So 6P is this group of blue color cells. Now if I take another series of cell and all this are negative from the top, and if we again connect their bottom like this and their top like this through a wire, then this is again a 6 parallel group but in reverse order. Now if I connect this positive with this negative like this, then basically what we are creating is a series connection of cells. So this is a configuration which I will call as 2 series and 6 parallel. So we can write as 2S6P. Now if I add one more such combination where I have all the cells connected positive on the top, and they are again connected in parallel and connected like this in the bottom, and if I now connect this part, this negative with this positive, let's say this configuration will be a series configuration, and this will be 3 series 6 parallel. So this is how the electric vehicle battery packs are created, and it can be as high as, so if you see the overall electric vehicle battery pack, it can be 96 cell series and maybe X number of cell in parallel. For example, let's say 4 number of cells in parallel. So there are around 400 cells in this kind of an electric vehicle battery pack, and because per cell voltage is around 3 or 3.5, we can consider that multiplying with the number around 100, this will produce 400 volts battery pack. So this is the configuration for an electric vehicle battery pack. How this battery pack is actually arranged in case of automotive. So inside an automotive, how this cylindrical cells. So let's consider this is one such module. So one module consists of many different cells connected in series and parallel, and there are many different modules like all this, and all these modules will be also connected, and that will together form a battery pack. So this is the overall configuration of an electric vehicle battery pack, and therefore you can see that how high voltage battery packs are built for an electric four-wheeler. So let's quickly move ahead and let's find out how much is the highest battery pack voltage level till now available. So we have figured out that high voltage battery pack will be efficient than low voltage one, but how much is the high voltage? So we usually you will find around 400 volt or 300 volt of voltage level for an electric vehicle system, but people are now trying with higher and higher voltages as well. So one of the commercially available vehicle is Porsche Taycan, and this is having 800 volt battery. So what are the advantages of such a high voltage battery pack? So this is one of the image of Porsche Taycan, and you can see in this model all these batteries are configured like this. So whatever you see, the orange color are the cables running through different modules of a battery pack, and different modules will be consisting of many different cells connected in series and parallel, and together they are going to form one unit of a battery pack. What are the advantages? So the advantages are the high voltage system can give consistent high performance, right? So for example, if you take a very low voltage battery system where it's a, let's say it's a 36 volt or 48 volt system, that voltage range, right? So the 48 volt is nominal voltage. When the battery is about to be at, let's say 20% of the charge level, that 48 volt may reduce actually to 40 volt, and this may actually hamper the performance or actually affect the performance in a way such that the top speed of the vehicle may not be maintained when the charge or the percentage level of the battery is 20%. So if the battery voltage is enough high, this performance cannot be compromised. So this is one just example of how low voltage battery systems will affect and how high voltage battery systems can provide the consistent high performance throughout the range of state of charge of the battery, starting from full charge battery to fully discharged battery. The charging time is also going to reduce because the higher voltage chargers will be actually required to supply lower ampere of current. And when you consider the lower ampere of current, the battery capacities are in ampere hours. So if the amperes are lower, the battery can be actually charged in a less amount of time. So this is just a comparison with reference to higher ampere hour and the low voltage battery pack. Now, what is the another advantage? So another advantage is we are going to use less number of cells, and the space and the cabling are going to be reduced, right? So the heavy cables for higher current application will not be there in case of a high voltage battery pack. So the weight and installation space for those cables, which are shown in the orange color over here, they will be actually one of the greatest advantage. So handling and space and the cost of the cable will be reduced comparatively. So this is about a high voltage battery pack. Now let's learn more about why do we need DC-DC converter in an electric vehicle. So as we have listed out, there are more than one reasons. So let us first figure out. So we know that there are auxiliary loads which are operating at a lower voltage, and those auxiliary loads like the lighting, horn system, audio system, telemetry and so on, they require a lower voltage to operate. So therefore we need a DC-DC converter. The other reason is battery to charger station compatibility. So for example, you have an electric vehicle which has 400 volt battery pack, and your charger station is going to provide you, let's say, 300 voltage output. Now in order to match your battery voltage with the charger station output voltage, you need a DC-DC converter there also. So this battery to charger station compatibility is another application of a DC-DC converter inside an electric vehicle. This is again what we have seen in the earlier block diagram. To connect the high voltage traction battery with the low voltage auxiliary battery, there will be a DC-DC converter required. And you can actually use the low voltage, less costly battery with a high voltage motor system. So for example, in a hybrid electric vehicle, you can use 400 volt motor system. So using a 400 volt motor system can be advantageous, and when you have a 400 voltage battery pack for a hybrid electric vehicle, the cost may be very high because you need more number of cells in series. So if you want to use a low voltage, less costly battery pack, then you can actually have a 48 volt battery system supplying 400 volt bus. So you can have a 48 volt to 400 volt DC-DC converter for driving those higher voltage motor, and that is where you can say that you have a DC-DC converter which will actually reduce the number of cells which are required to be connected in series. So this is one of the application where DC-DC converter is required, and the last and final application can be combining more than one type of energy resources. So there are limitations of the battery, and people are adding ultra capacitors or fuel cell solutions along with the battery. So in an hybrid electric vehicle, you can have a combination of ultra capacitor along with the battery, and you can have a fuel cell also added with the battery. Now when you are going to combine these two, the ultra capacitor and the fuel cell will require a DC-DC converter in order to match the characteristics of the load and their own fuel characteristics, or their own voltage, current, or charge discharge characteristics. So here also you will need a DC-DC converter. So these are some of the areas or some of the reasons why EVs need a DC-DC converter. So let us consider an image, and let's try to see where exactly are these DC-DC converters located in the arrangement of electrical system for an electric vehicle. So this are shown in the figure like this. So here you have a higher voltage battery system, and this is going to be 400 volt battery system. Now this 400 volt battery system can be reduced to 48 volt battery system by a DC-DC converter, which is 400 volt to 48 volt system level DC-DC converter. Now you have a 48 volt bus in the yellow color over here, and this 48 volt can actually supply the 12 volt regulated loads, which can be a water pump, an AC compressor, or maybe any of the other loads. So here also you need a DC-DC converter module which will translate 48 volt to 12 volt regulated output. Now instead of a regulated output, you may require a different type of a DC-DC converter which will maintain just 12 volt as a fixed ratio. So whatever is the voltage available over here, according to the ratio of this converter, this will maintain 12 volt, and there may be a different types of load for this type of converter. Now you can actually directly feed 48 volt over here to the some of the loads which are going to need directly 48 volt, and you may need a 48 volt to 48 volt DC-DC converter as well. Now you may be wondering that why do we need a 48 volt to 48 volt converter? So what is the purpose of using that? We are not changing any voltage level, right? But actually this is going to change the power which is available to the 48 volt load. So from the bus to the load, it can actually regulate this, right? And so if you understand this DC-DC converters, there are two major categories. One is a voltage translator, we call it as a converter, where it can be 48 volt to 400, 48 to 12, and so on. And other category is called actually the controller, so which is called a voltage regulator as well. So the voltage regulator will maintain the 48 volt to the load irrespective of change in the input 48 volt, and it will also control what is the power applied to the load. So 48 volt regulated will actually control the current which is fed to this load and therefore the power of this load. So for example, electronic power steering or headlamps and other systems which may require a control or a regulation, and these are the type of that DC-DC converter. So in an electric vehicle architecture, you need a system level DC-DC converter or a load side DC-DC converter and so on. So these are the three major categories which we are going to see. So the first one, as we have seen, charging station compatibility DC-DC converters, the conversion compatibility such as this one, which is going to change 400 volt to 48 volt, and there will be some kind of a delivery DC-DC converters which are actually going to deliver the power to the load. So these are three major categories of DC-DC converters used in electric vehicle. So now let us take an example of 48 volt and 12 volt configuration. So if we see this example here, we are able to see there is on right side of the image we have 48 volt system where you have 48 volt loads connected between positive and negative wire like this, and this can actually include the 48 volt battery as well, and you have a 48 volt starter generator, or we can say the high voltage starter generator. And on the other side of this DC-DC converter, which is the main element over here, you can have a 12 volt system, positive and negative. So the 12 volt and ground can feed the 12 volt load connected in parallel along with a 12 volt starter, which can be a cold crank and which is going to be supported by 12 volt battery. So this is called a 12 volt and 48 volt hybrid automotive electrical system, and this is also going to be require a DC-DC converter, and this can be actually inside an IC engine vehicle or maybe an hybrid or electric vehicle. So DC-DC converters are going to be used popularly for EV and HEV applications. So this is the end of first video, and in the next video we are going to learn about how to use Ansys for design of such DC-DC converters, what are the available options, how we can simulate this, and what are the different design stages in which the Ansys tools can be beneficial.